Like all this like
Acid-base titrations. We will be reviewing the basics of titration, which we learned about in Unit 4. I know that was a while ago, but we're going to go back over it. Starting off with the basic construct of how the lab looks. You have your burette right here. It's held up by the burette clamp on the ring stand. And you have your flask down here that holds the analyte. The analyte is the one with the unknown concentration. Also, you put in there usually an indicator that's going to tell you when you need to stop your titration. In the burette goes the titrant, which is the one with the known concentration. Now, what you do before you begin your titration is you do an initial volume reading. You write that down and you say, this is how much I'm starting with. And then you do a final reading once you reach the equivalence point. So you know how much volume was added to the flask. And with the known concentration, then you can figure out the unknown concentration. Because do remember, you did measure the volume in here, so you do know the volume of the analyte. So these are the basic constructs here. The titrant is the standardized solution. It's the known concentration. The analyte's usually the unknown in there. That's going to be in the flask. And it's basically a laboratory way of detecting and figuring out the concentration of a solution that you don't know. Now, what we've covered so far in Unit 4 was the strong titration stuff. So we haven't looked at the weak strong titration stuff. So we'll be building on old concepts from Unit 4, moving into new concepts for Unit 8. Now, a strong acid, strong base titration, just reviewing quickly what the net ionics look like. Looking here, this is the molecular equation, because remember, we have to also distinguish titrations are going to be neutralization reactions. It's going to be an acid plus a base giving you water and salt. This is different than weak acid-base equilibrium. Weak acid-base equilibrium is finding how much ionizes when it's in water. Remember, weak acid-base equilibrium is always water is one of the reactants. Okay, here we're actually producing water. Water is one of the products. This is a completion reaction. It does not have an equilibrium position. It goes to completion, arrow in one direction. Now, to remember how to do the net ionics, you have to know like what's going to break apart. Strong acids break apart into their ions. Strong bases break apart into their ions. Anything that's a pure substance stays together, like liquids or solids. And gases. And then, of course, here, that's a soluble salt. Soluble salt, so it breaks apart into its ions as well. This would be the complete ionic. So we wrote out how it's going to look, but they don't really care about the complete ionic. They want you to be able to tell them the net ionic of what is going to react. Yes, for the net ionic, we remove the ones we call spectators. The spectators are the ones that aren't participating in the reaction, like the chloride here. Also, sodium is a spectator. It is not participating in the reaction. It's just floating around in between the waters. So the net ionic reaction is going to be hydrogen plus hydroxide gives you water. And notice here, this is for strong acid, strong base. It is always 1 mole of hydrogen plus 1 mole of hydroxide gives you 1 mole of water. That is the net ionic that you would want for a strong neutralization. So the first question of weak acid or of acid-base type problems usually is a net ionic of some sort. So you want to have knowledge of them. Let's look at a weak strong example. We have sodium hydroxide strong base plus acetic acid, which is vinegar of weak acid. Looking at this one, The molecular equation. Remember, the things that are strong will dissociate, break apart into their ions. The things that are soluble will also dissociate. So here, the sodium hydroxide dissociates because it's a strong base. The acetic acid, though, is a weak acid. It does not separate. You have to keep it together because it only, a small fraction of it actually ionizes. The water stays together. The sodium acetate, though, does break apart. On the solubility rules, acetates are always soluble. So if you look here, the only spectator is sodium. It cancels. So this net ionic looks different than the strong-strong. That is because you have the hydroxide plus the weak acid, the entire weak acid. Gives you the water, but also the conjugate base. That is also a product here. This hydroxide is going to rip off the H, produces the water, but that means that acetate is left floating around in there. And that's significant too because acetate happens to be a basic anion, so it's going to react with water and create a little bit of hydroxide on its own for secondary reaction purposes. But for a net ionic here, OH plus the weak acid, keep the weak acid together, you get water and then the conjugate base. All right, this one's an interesting one, and that's why I put it up here, is how ammonia reacts with hydrochloric acid. Hydrochloric acid is a strong acid, and ammonia we know is a weak base. So here's the molecular. Actually, I broke it up already. This one you would break up apart to H plus Cl minus. So as you can see, the chlorides end up canceling because they're spectators. So the net ionic of this one looks interesting because water isn't even in it. It's just NH3 plus H gives you NH4 plus. But this would be the neutralization here for the ammonia reaction. So the weak base ones that have the amine type groups on them, they do look slightly different. We're talking neutralization here. Last one that I want to show you is not one that is used all that often, but it is a possibility. Remember, magnesium hydroxide is one of the insoluble hydroxides. Most of them are, except for your strongs. But you could react it with hydrochloric acid. Even the solid will react with the hydrochloric. We do have chlorides as our spectators. They would cancel out. But that leaves you with the magnesium hydroxide solid, the hydrogens reacting, the magnesium ion, and the water. So that's how that one would look if you were actually wanting to react a solid with the acid. Okay? All right, now let's talk titration curves, the actual graphs themselves. Titration curve is the plot of the pH of the analyte as the standardized solution is being added. And usually, this one's an acid being titrated by a base, and it forms like that S shape, where you have the long vertical inflection point in the middle, like here, this inflection point, like so. And you put the volume of the titrant on the bottom, and then you have the pH over here on the y-axis. So that's the general construct of how the acid being titrated by the base curve looks. One important point that we always figure out on our titration curve is called the equivalence point. Just recalling, what is the equivalence point when we're referring to acids and bases? It is the stoichiometric point where the hydrogen reacts with the hydroxide to give you water, where the moles equal the moles at the equivalence point. So moles of hydrogen now have equaled the moles of the hydroxide. You're at your equivalence point, and you have just water. For redox titration, remember this is more about the moles of the transferring of the electrons, but here for acids and bases, we're talking hydrogen, hydroxide are equal. In equal amounts, that means we have water left over. That's it. This graph is showing you a strong base with a strong acid. It is kind of the reverse of the previous one, but that is showing you the equivalence point here. Equivalence point is the middle point of the long vertical inflection point. And for a strong, it's always going to be right here at 7. But as you can see, it starts out pretty flat, then it dramatically decreases, and then it comes over like so. So it's got the same type of idea here, but it's just opposite of the acid being titrated by the base. All right, let's go over the basic features of the titration curve. First thing to note, for a strong acid, strong base, it's going to be a pH of 7 for the equivalence point. Right there, smack dab in the middle. Then, that equivalence point should be close to the end point of the titration with a good indicator. So if you chose a good indicator with the changing in the right pH, you will probably, your endpoint will hit your equivalence point and almost be completely accurate. Last but not least, the equivalence point is the point of inflection on the titration curve. This long vertical point, like so, that gives us our 7 here on our titration curve. Let's talk about the endpoint. What is the endpoint? Marks the point of the titration when the indicator changes color. And if you pick a good indicator, it should change color at your equivalence point, because you should know which types you're dealing with when you're doing your titration. And you've done enough research to make sure that you've picked an ideal indicator. However, the endpoint is not necessarily exactly when the stoichiometric moles equal to moles, that equivalence point, but you try to make it as close as possible so you get accurate data. All right, indicators. Phenolphthalein, we talked about some of them in Unit 4, but let's refresh. Phenolphthalein is a common one used in the lab because it's clear or hot pink. So you can see the pH range. 4, it starts to turn right here around 8, that light pink. This would be when you would stop your titration. So you can see on the nice graph up there, you want to stop the titration when you're using phenolphthalein when it is just a faint pink color. However, phenolphthalein isn't the end-all be-all of indicators. There are other ones like methyl red. This one has kind of an array of colors, going from a dark red over here at pH of 2, getting into some orange, getting lighter into yellow until you get over here to pH of 10. So that one has more of a rainbow array of your warmer colors, though, red, oranges, and yellows. That one kind of reminds me of universal indicator, which pretty much does the entire rainbow, like your pH paper would do. So that one's kind of fun. Another preferred one I use in my lab, because it's good for strong, is bromothymol blue. It's yellow and blue make green, and the green part is only a narrow part, and it's right around 7 here on our pH scale. So it changes to green just briefly. You have to be paying very good attention though, so you don't go straight over to blue, and you make sure that you stop your titration at the right point. With bromothymol blue and phenolphthalein and methyl red, there are many other indicators out there, as you can see on our nice lovely chart here, and this isn't even all of them. So really, when you're planning your lab and deciding what you're going to be investigating, you would need to pick a good indicator that you know would measure your information correctly and would change colors at the right pH. But there's plenty of them out there to choose from. All right, now we're going to talk about the titration curve of a weak acid with a strong base. There are definite features that are different about them. They look similar because it looks like the S thing with the inflection point and all that, but there are serious differences in characteristics between a weak acid strong base and a strong acid strong base titration. The first thing you should notice is that the equivalence point is above 7 here. It is not at 7 anymore. It is above 7. A weak acid, strong base. Over here you can see it's 8.73. The pH will always be above 7 if you're titrating a weak base with a strong acid. The next thing you should see is there's something called a buffer region or buffer zone. The buffer zone is right here at the beginning of the graph. And it pretty much goes all the way over here to the equivalence point. This is the entire buffer zone. Now I don't necessarily agree with this arrow here, but about halfway, exactly halfway in the buffer region, that's called the half equivalence point. The half equivalence point is going to be mid part of the buffer region, and it's halfway to the equivalence point, hence the name half equivalence point. And the significance of it is at that midpoint, at half equivalence point, the pH equals the pKa. The pH equals the pKa. Now remember, anytime it's pK, P in front like this, that's negative log of the Ka. Like here, this is negative log of the hydrogen. So that P in front means we took the negative log of the Ka. Now if they gave you the pKa, the half equivalence point on the titration curve, but they didn't give you the Ka, you could always figure it out. So that is an option. It is the midpoint of the buffer region. So 3 distinct characters, different than the strong. Another thing to notice too is on this buffer region, it's a little bit more of an inclination in the slope. It's not as flat. Whereas the beginning of the titration curve for strong is usually down here a little bit lower in the pH, and it's a lot more flat. The buffer region actually has more of an inclined slope. But it usually also starts at a little bit higher pH. Like here it's starting a little bit higher than, say, the strong one. The strong one would look more like this. That would be more like the strong curve. Like so. So they definitely look different in their appearance. Now here is how a weak base would look with a strong acid. Similar in of the fact that it has that same shape where it starts out at the higher pHs and then it does the inflection point. But you should also notice that the pH at the equivalence point is lower than 7 now. Whereas for the weak acid strong base one, it was above 7, it's now lower than 7. For this particular example, it's 5.28. The halfway point, half equivalence point, is actually equal to the pKa of the conjugate acid. Because remember, this graph is measured in pH, it's not measured in pOH. So when we do that, go to that half equivalence point, we're looking at the pKa of the conjugate acid. In that case, our conjugate acid happens to be our ammonium. However, this is the problem with the base problems, is because everything's measured in pH. You can convert stuff over to pOH if you want to make it easier. pOH at the half equivalence point is the pKb of the weak base. But you'd have to start by first converting the pH to the pOH, and then you can work backwards to the pK or to the Kb that way. You can also see that the buffer region up here, because it has a buffer region right here, this is a buffer region, it is also a little bit more of a slope, like a descending slope, negative slope, whereas on a strong one it would be a little bit more flat before it goes down. Okay? So that is a difference there between strong and the weak. And actually, the strong would probably be up a little bit higher in the pH starting up there before it starts declining a little bit as it gets to the inflection point. Now a diprotic acid. Diprotic acids, they look different in terms of the neutralization. Why? Because they have 2 H's in their acid. So like a diprotic acid would be like H2A. You have the 2 protons to get rid of. But they neutralize one at a time. Remember, it's a stepwise fashion. One H has to be pulled off first from all of them, then the second H. That's why you see two equivalence points up here. It actually takes, this is to remove the first H, and then this one's to remove the second H. Now here, this is going to be the pH is equal to the pKa of the first one, the first Ka, and this one would be the pH equals the pKa of the second one. You have two buffer regions, you have two inflection points, that means you have two equivalence points here. It's basically two titrations on the same graph is what we're looking at for a diprotic acid. So I'm sure you can now imagine what it looks like for a triprotic acid. The triprotic ones, so you can see here, have three buffer regions, three inflection points, and three equivalence points. You're starting here with your triprotic acid, like so. Here is the first half equivalence point where the pH equals the pKa of the first one. Then here's your equivalence point, your first equivalence point. Now for the second H, as you can see, here you go, midpoint, where we have the pH equals the pKa of the two. Here is the second equivalence point. Then we have the pH equals the pKa of the third one and the third equivalence point. I like this because it shows you what's happening here. When you get to that halfway point, the acid is equal to the conjugate base here. So we'll talk about that feature as we get more into the titration problems, because that's where we're about to start, our titration problems. Now there's a mistake on this graph, so go ahead and correct it. This should say NaOH right here, because this is strong base reacting with a strong acid. This is a strong, like I said, this is a little bit more flat down here, a little bit more flat. Okay, starts lower. The pH at the equivalence point does happen to be 7 right here in the middle. So before we start our problem now, I wanted to show you like what we're going to be doing and what is expected for you in terms of titration problems. What they have you do is they have you track the pH at certain points along the titration. So first thing, they always like to know what is the initial pH. So the initial pH, that's important before any of the base has been added. They'll have you calculate that. Then they'll have you calculate somewhere in the buffer region. And we're going to be working at 10 milliliters, so that'll be in the buffer region. Then they have you look at the equivalence point, calculate that. If it's not a strong, if it's a strong, it's automatically 7, so you don't have to calculate that for strong. But if it's a weak strong, you do have to calculate it because it'll either be above 7 or below 7 depending on what your titration looks like. And then they usually want you to calculate excess, like up here at 20. After you've gone past the equivalence point, what is the pH now? So that's what we're going to work our problems along the pH, along the titration curve, figure out the various pHs at those different points along our graph. Now for the strong scenario, it's not too bad. It's pretty easy. Because strong is the one hydrogen plus the one hydroxide. Everything's 1 to 1. And we look at the moles equal to moles and all that. 1 to 1 ratio. So according to our net ionic, it's very easy to figure out what, after so much has been added, what's left over in solution. However, we figure out what's left in solution. That's not canceled out. But we always have to factor in this idea of the new volume, because as you're adding stuff to your titration, you keep adding new volume, that changes concentrations. Changes concentrations because we know that molarity is moles over liters. So besides calculating the moles at each point, we're going to have to figure out the new volumes at each point so that we get the correct concentration in order to determine the pH. Strong, strong is not hard at all. Weak, strong, then we get a little bit more in terms of our calculating. So let's start with the easy one. Let's look at strong, strong. And so many people look at this and they go, oh, it's really not that hard though. We have a titration of a 0.2 molar hydrochloric acid with a 0.15 molar sodium hydroxide. We're starting with 10 milliliters of the hydrochloric, calculating the pH after the volume of the sodium hydroxide has been added. Well, at this point, this is the initial, right? We're starting off with where 0 sodium hydroxide has even been added. So how do we find the pH at this point? What drives the pH? What specific ion do we look at for pH and its concentration? Which one's the important one for pH? Hydrogen, good. So really, we need the negative log of our hydrogen. Do we know our hydrogen at this point? We should, right? Because we didn't add any hydroxide. So what do we start out with here? What is our hydrogen concentration? If we have 0.2 molar of HCl, that means this is really just H plus, because HCl is one of the strong ones. So it completely ionizes, completely dissociates. So for this one, all we really need to do is negative log of our 0.2, and that's going to be our starting initial pH. Now what does our starting initial pH, what does that calculate to be? Yes, we're going to go with that, except for there's 3 significant figures in our concentration, so I'm going to keep it at 3 decibel. So 6.99 looks good to me. That is our initial pH to start off with at the bottom of the curve. So easy enough. Not too bad. Now let's look at after 10 milliliters of hydroxide has been added. All right, this is where we do have to do a few stoichiometric type calculations. We need to compare the moles of each. If you look here at our net ionic, we have hydrogen plus hydroxide. That's going to give you 1 water. And we're starting off with, for the HCl, we have 10 milliliters. And our concentration, 0.2. And for our hydroxide, we have 10 milliliters. And we have 0.15 molar. So before we can do anything, we have to figure out how much of each is reacting here and which one is left over. How many moles is left over in solution? And if you look at these numbers, you should be able to visually see which one's going to run out and which one's going to be left over. Is hydrogen or hydroxide going to be the one left over floating around? Hydrogen, because there's more of it. But we need to figure out how much hydrogen is left over. So you can do this one of 2 ways. You can use your molarity equation to figure out the moles, or you can use dimensional analysis, which is what I prefer. So we need to change these over to liters, right? Got to change it over to liters, so do that. Divide by 1,000. So we end up with 0.0100 liters, and I have 0.200 moles for 1 liter of H plus. That's going to give me 0.00200 moles H plus. I'm going to do the same here for my hydroxide. 0.0100 liters. 0.150 moles of the hydroxide for 1 liter. That means I get 0.001 150 moles hydroxide. So if we go ahead and subtract those, like do the subtraction here, how many moles of the hydrogen will be left over? Zero 0.00050 moles H plus, right? Because if one mole reacts with the other mole to give you water, you have a little bit of extra hydrogen hanging around. Sure.
Well, where did you get the negative sign for the 0.00150 mole OH minus?
I'm subtracting the two so I can figure out what's left over.
Oh, yeah, okay, sorry, I didn't see it like that. My fault.
No problem. So now we know the moles of H that's still floating around inside our flask. What else do we have to take into consideration before we calculate the pH? What also has to be factored in and calculated for? The moles doesn't determine the pH. What determines the pH? Not the moles of hydrogen, but the concentration. So what also changed about our concentration besides the moles? Our volume changed, right? We ended up having 10 milliliters of acid being added to 10 milliliters of base. So our new volume, guess what that is? 20 milliliters, which is 0.0, no, only 1 0 there, sorry. 0.0200 liters. So we need to take this and divide it by our new volume. That will give us the concentration of our H+. Because remember, molarity is moles divided by liters. So what is our new concentration here? What is the new concentration? Let's calculate. 0.0005 divided by 0.02. What is the new concentration for our hydrogen at this point in the titration curve? Yes, that is correct. Now, it's simple. It's negative log of hydrogen. It's going to give us our pH. So what is the negative log of 0.025? Yay, that's correct. 1.60. Looks good to me. So our new pH, it went up just slightly from 0.699 to 1.60. Not dramatic. But like I said, it stays pretty flat there in the beginning of the curve. For a strong at least. Now for the easy part. Let's calculate the pH at the equivalence point. This is the toughest one of them all, the equivalence point. We have a strong acid and a strong base. So what would be, how do we calculate the pH of the equivalence point? What is the pH at the equivalence point? It is 7. This one you just have to know. Yes, because strong is always going to be a pH of 7. And if you want to get into the weeds on that, it's because the strong have the neutral salts. So neither one are going to react with water, and that's why it's 7. Right? Got it? The neutral salts?
Yes. Yep.
Cool. All right. Now let's talk about excess. Getting past the equivalence point, because now we're going up to the top part of the curve. There is more hydroxide than there is hydrogen. So now we have to calculate the new concentration of the hydroxide, which means we're going to have to factor in how many moles are left and what is the new volume at this point. How many moles of hydroxide are left and what is the new volume? Then you can do 14 minus the negative log of hydroxide to get your pH. All right, let's do it. So we know, and remember, what are the amount of moles of H plus in there? Because remember, that's the analyte, so we only put a certain amount in there. What is the moles of the H plus? How many moles of H plus do we have in there? What's the moles of our H plus? Huh? 0.002. Yes, this was the moles of our H plus in there. All right, now we have to figure out how much hydroxide has been dumped in there in terms of the moles. 20 milliliters, 0.0200 liters. And we have our molarity, 0.510 molar. So how many moles of hydroxide have been added to this flask? Let's go ahead and figure that out. And what do we get here for the moles of hydroxide that have been added? Now, can we figure out how many moles are left? Because remember, 1H plus the 1OH minus gives you 1 water. So yeah, subtract this out. Minus out the moles of the H plus. How many moles of our hydroxide is left? We have 0.001 moles of OH left. That's the first part, is figuring out the moles. We still need to figure out the new volume. What is our new volume here at this point? We added 20 milliliters of our hydroxide. Now what else was in there? How much of the acid?
10 milliliters.
10 milliliters of our acid. So our new volume happens to be 30 milliliters. And so we want to change that over to liters, 0.0 liters. Now, all we have to do is divide this by 0.0300 liters. This is going to give us the concentration of the hydroxide. What is the concentration of our hydroxide at this point along the curve? Yes, let's calculate that number. I know it's a number, but I want you to calculate the number. So what do we get there? Yes, 0.333. That's great. Exactly right. So our concentration here, 0.033 molar. Now all we have to do is do the 14 minus the negative log of the hydroxide, and that's going to give us our pH. So let's go ahead and do that. We have 14 minus negative log of the 0.0333. And our pH is 12.522. Well, that's what I got when I calculated it. Is that what you got? So it's in the upper part of the pH now. You saw that? Definitely up there. Alrighty. Yes, definitely close on these. Maybe a few rounding differences. But figure out the pH along the different titration points. This is strong, strong. This is the easier one. Now let's start looking at the harder. Now this portion of the notes, I left you space to write the stuff in at each one. And then on the next page, we'll do the calculating. So here under 0, what you want to be writing is that this is a weak acid equilibrium problem. That's what you need to be writing in here. This is a weak acid equilibrium problem. The only thing you have in there is a weak acid with the water. None of the base has been added, so it's just the first part of the weak strong combo is always going to be weak acid. The second part is a buffer problem. Now we're going to skip this for now because we don't know how to do the buffer stuff yet, but we will come back to the buffer stuff and figure out how to do this part later. This is going to be a buffer problem. And actually, in some ways, the buffer problems are a little bit easier. The real dicey part is at the equivalence point. I think this is the toughest part of the curve. This is going to be a weak base equilibrium problem. The reason why that is when you've neutralized all of the acid, you've added enough base where you've neutralized all of it. The only thing left floating around in the water happens to be the conjugate base. And the conjugate base of a weak acid we know is going to be basic and it's going to react with water. So it becomes a weak base equilibrium problem. Now the 20, luckily, past the equivalence point is still just an excess problem. It is just like the one we just did. So this one is very easy. Just like the last one, this part doesn't change. This part's pretty easy. Excess OH problem. So that shouldn't be too hard. These are the basic things that you're going to see for a weak combination. Now, if we're doing a weak base with a strong acid, it's just going to be the opposite. The 0 is a weak base problem. The 10 is still a buffer. The equivalence point now is going to be a weak acid problem. And then the 20 is still an excess for the H+. So it just goes the other direction. All right, so looking here along the pH, titration, how does it look? You're basically doing like the initial point here. You're going to do somewhere in the buffer region, wherever that is. You're going to do the equivalence point, and then you're going to do an excess over there. So those are the main 4 points along the pH of the titration curve that you would be calculating as we're doing the weak acid with the strong base. All right, so here we're going to work this weak acid problem because if 0 milliliters have been added, basically all you have in there is the acetic acid and water. And yes, it's going to establish its equilibrium position in water and ionize a very small amount. So all you have to do here, have our acetic acid reacting with the water, because there is no hydroxide's been added at this point. We're going to get hydronium and our conjugate, like so. Here is the reaction. Now, you can do the rest of the rice table if you want. I skip over here now to doing here is our initial amount. We know we're going to subtract out X from that. We don't care about the water. This is going to end up being X. That's going to end up being X. Then all we have to do, write out the equilibrium expression. Ka equals the first product, concentration of the hydronium, times the conjugate base over the original acid, which is the reactant, like so. And then we plug in, we get 1.8 times 10 to the minus 5 equals x squared over 0.2 minus x. We take out the x, you know, for the 5% rule, remove x, and we calculate looking for this hydronium, because we want that for the pH. We need that x. X equals the hydronium, and we figure that out. What is our concentration of our hydronium? Concentration of hydronium. What do we get there?
Right, maybe.
1.9 times 10 to the minus 3?
Yes.
All right, Bowler, good. Then all we have to do is the negative log of our hydronium. That's going to give us our pH. So do that, negative log 1 times 10 to the minus 3. And what is our pH to begin with of this titration curve?
.7.
2.72. You get 2.72, which is correct. Sure, go ahead.
So this is on the AP exam. How much time do you think we would have for this question? I know it's not time for specific problems, it's time for the whole section, but like on average, if we're doing this problem, how much time do you think we would have?
Well, like you said, some of the free response questions may take you 30 seconds and other ones might take you 2 to 3 minutes. But this one should probably take you about 2 to 3 minutes.
Okay, yeah. That's fair.
Okay, good. So there we have that one, good. All right, now we're skipping the buffer problem for now. Okay, we're not going to get to it because that's one that you're just going to, do the asynchronous notes for. And we'll come back to talking about buffers next week. We're going to just look at and outline the process at the equivalence point because there's a lot of steps to it. We're not going to get to actually calculate it today, but we're going to outline it. All right, at the equivalence point, there's a couple things you need to think about. We already know how to do this, but we need to think about it. Equivalence point means the moles of the hydrogen and the moles of the hydroxide are equal. They are now all turned into water, right? And if it's a weak one, the moles of the HA are equivalent to the moles of the hydroxide because it's going to pull off the H every single time to produce water. So what is in solution that drives the value of the pH? Because remember, this hydroxide is going to pull off this H. That's going to leave behind our conjugate base. So our conjugate base is floating around at the equivalence point by itself with water. Is it just going to sit idly behind and do nothing? No, it's going to react with water. So it turns into a weak base equilibrium problem. So here, the first reaction goes to completion. We end up with our water left at the equivalence point, our conjugate base left at the equivalence point. Remember, the anion of the weak acid is a base. So that acetate isn't going to sit around and do nothing. It's going to start reacting with water. And what we know that it's going to make it basic. And that's why our equivalence point is going to be above 7.